for example, around 40% for proteins is very different from lipid head groups and deuterated lipid head groups. So we can actually tune the system to see in principle different components. Okay. So when you're looking at these, again, starting again with the bilayer, and again looking at different contrasts, mixtures of H2O and D2O, this is sort of the scattering profile that one can see from the reflectometer. This can be converted into a scattering length density profile, which essentially gives you an idea of the scatter as you move away from the gold surface. So it's sort of labeled here. You see the scatter from the gold. You see a region which represents the tether scatter, and then the inner and outer leaflet of the membrane can be easily picked up. The head groups are observable, and then the bulk solvent. So as you go away from the bilayer, we can see each region as one would expect from an assembly. And so this again just shows this as a cartoon. So you've got your gold here scatter, your tether, which is an aqueous region, which sort of matches the scatter of the bulk solvent. And then you have a differential scattering here from the lipid bilayers, with the hydrophobic tails of the lipids having slightly different scatter than the head groups. So you can see the head groups, the tails, and then the solvent on either side. So just as as a summary, we can use these three methods together to potentially or to gain some information about the assembly of these systems, and then something about the structure. And so we use the impedance and the surface plasmon resonance because they're of high sensitivity and fairly rapid measurements to get a sense of the integrity of the system and the amount of material on the surface. And once we've optimized this system using these measurements, the reflectometry can be done with